Thanks. All right, let's begin with a word of prayer. Dear Heavenly Father, we just thank you for this day. Again, Lord, thank you for the students. The semester is about to start. Just pray you be with us this semester. Just do our best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So it's nice to see all of you. So many people here today. No, I know. The Trump will do what he does. But the show must go on. Okay, so basically in here, I'm going to talk about the syllabus a little bit more next time. I'm just go straight into material this time. Well, all right. What's that? Do the syllabus because no one's actually going to watch this? Hey. That hurt. I have feel. Is that still locked? Really? Yeah. Okay. It's probably, you know what it is? It's probably the college algebra people who are realizing, oh, what? No. Let me get some more math on the board. Make sure they don't try. Okay, so getting back to focus. So if you guys have had me before, you kind of already know, but I try to write a course planner for, for the different courses. Did I post a course? I don't think I posted anything yet. I will hopefully later today post a day-by-day schedule of what we're doing in here. And I usually try to follow that more or less closely. Just to give you kind of an overview, we're going to have a quiz on the 3rd of February. That's the first kind of major thing. The first homework will be due next Monday. We have homework due about every week. Test 1 is February 24th. I think I have 2 tests in here. Yeah, 2 tests. The tests will be worth 150 points. That quiz is worth 100 points. So the first quiz is kind of like a little mini test. It's basically just focused on the computational core. So the first test is a little bit less proofy, a little bit more computational. Which isn't to say there won't be proofs on the first quiz. It's just its focus is more on computation. There's 2 big tests. There's one quiz, one in-class quiz. There's a take-home quiz later that's about other things. And so anyway, I'll let you guys read the syllabus once I post it. It's kind of hard to do it at the moment. And then you can send me questions or ask whatever. I have office hours. I do have office hours. And I thought I printed the syllabus out, but I don't seem to have it. My office hours are posted on my website, so I just encourage you to go there. Oh man, really? Wow, that was loud. www.supermath.info. So if you go there, you'll find my schedule. I have office hours in the morning. I forget exactly when they start, but it's something like 7:30 to 8:15, or maybe a little bit before that. I forget exactly. There's those, and Monday through Friday, yeah. And then I have a block of time Thursday afternoon, so those are the office hours. And of course, you can send me an email anytime. Just to remind you guys, the office hours are to ask questions. They're not to come and study. That's not usually a problem with anybody, but some other professors like to have students like come and work in their offices or whatever. It's not. I like to have questions in office hours because some professors. I don't know who I'm talking about. All right, so let's get on with it then. So math. Let's talk about the math. What math are we doing here? This is, of course, the course in linear algebra, which is the study of, what is it the study of? That's a good question. I would say it's a study of linear structures. Some people would say it's the study of linear transformations, really, in their structure. I don't know, but I think we'll have a good answer to that question by the end of this course. That much I can say. So some basic notation, right? And here I'll use this for the real numbers. This is the notation for the complex numbers, the natural numbers, which is this in here. Opinions vary on that. This is the integers. And then, of course, you've got what? Rational numbers. Wow, this is fascinating, yes. A little bit of fine print here. What else do I need? P over Q such that what? P and Q are integers and what? Yeah, Q is not equal to 0. Those are rational numbers. So I assume you know what these things are. You know how to add them, subtract them, multiply them, divide them, all that good stuff. Now, there's one other extra new thing that we will use in here that I should mention, and that's this notation, n sub n. Now, by that, I mean 1, 2, n, all right? So that's just the first n natural numbers. I find that to be a convenient notation because we're working with that a lot in here, all right? We also like to talk about Cartesian products. What's a Cartesian product? So like a Cartesian product, if I have A, sets A and B, A cross B is what? It's A comma B such that what? By the way, what's this notation I'm using? I'm using set builder notation. I'm not going to belabor that. I think you guys know about sets and elements and such. I mean, you should. I assume you know that sort of thing. So let's see here. A is an element of A, and what? B is an element of what? B, right, yeah. And so what makes a Cartesian product is really just that the first component's the first component, and the second component's the second component, right? If I had AB and I had BA, those are different ordered pairs, right? It's an ordered pair. And of course, you can do this more than once, right? You can just as well talk about something like, for example, A to the n would be A cross cross A, which would be the set of n tuples, right? A1, A2, AN, such that what? Such that A sub I is an element of A for all I in n sub n. Or another application, like let's see, we can mix and match these things. Another example of some of this notation that we use. Maybe I want I and j to be indices, all right, and I want them to be allowed to run for, say, I want to let I run from say 1 to 2. Suppose I want j to run from say 1 to 7. I would say this is an element of what then? Here, you guys fill in the blanks. So if I runs from 1 to 2, I just put a 2 there. If j runs from 1 to 7, I put a 7 over there. And then this little statement right here captures this idea that I runs from 1 to 2 and j runs from 1 to 7. Now, if you want to write that in a less compact notation, you could say something like 1 less than or equal to I less than or equal to 2 and 1 less than or equal to j less than or equal to 7. But that's actually a lot more to write, right? Yeah, you guys can come and sit over there if you want. Wherever you want to sit, go ahead. It's no problem. I understand this is a weird day. I haven't said much. I just basically said the syllabus is not posted yet, but I will post it. And I try to let like one person tape every day. So since like 40 of you guys, probably just one day. She's got it over with. What was your name again? Jen. Okay. Thanks for taping today. Okay. So these are the basic, places we take numbers from a lot of times. We need to know what a Cartesian product is. This notation is useful. What else? What other basic things do we do with sets sometimes? We might talk about subset, talk about union, we'll talk about intersection, right? I don't think you guys know what those are already. So I will also post the notes hopefully a little bit later today. And so the first chapter in the notes is called Foundations. In this Foundations chapter, I have these definitions and more. I have some discussion of functions and things, which we don't need too much right now. There's a little bit more in the Foundations chapter than I actually want to focus your attention on right now, so I'm kind of annoyed with that. I haven't had a chance to trim out some of the fat. So I'm just going to try to stick to just the things we most need for our discussion, which is this, that, and let's see here. So something you might know less about, let me just glance at something here. Oh, there's my syllabus. Now I find it. So basically the first required thing will be the homework that's due next Monday, which I hope to post like today. still working on it. You guys know what real numbers are? Yeah, I mean, we know their properties at least, right? Constructing them, that's a harder thing. But we can at least talk about them and use their properties. Okay, so I guess I'll say this. All right. Sorry, this Trump visit's got me all out of sorts. I mean, don't get me wrong. I did sign the petition for him to be on the ballot. I think it's hilarious. Sorry. All right. So there's the complex number systems. I probably should talk a little bit more about complex numbers. Have the form what? A plus IB, such that A and B are real numbers, right? So for the examples in the first arc of this course, they're basically going to use real numbers, complex numbers, and then sometimes we'll also use what are called finite fields, right? So I want to just kind of give you a brief introduction to how to do arithmetic on these things if you haven't seen it before. Complex numbers are actually pretty simple. You work with them the same way you work with real numbers. What's the one kind of catch? What is it? It's I squared is equal to -1, right? So let's see here. As an example, if I have A plus IB times C plus ID, and we multiply, how's that work? We just distribute, right? So I got AC plus IAD plus IBC plus I squared BD. And then it's customary to collect things and write it in the so-called Cartesian form, right? So the Cartesian form here would be AC minus BD, right? Plus I times AD plus BC, right? So this is how we multiply complex numbers, right? A little bit more, let's see here. So if Z is X plus IY, right? That's a complex number, or complex variable if you like. What's the conjugate of that? Usually write Z. Stars or bars? I can't remember. I got a bar, I got a star. I don't know. It's just chivalry dictates I have to put a bar here. So Z bar X minus IY. See, that's the most annoying reason I could have picked in Lorenzo's opinion. Let's see here. So I did such. But anyway, so that's the conjugate, right? This is important because if you multiply Z bar, what do you get? We get, X squared plus Y squared. The imaginary part cancels out, right? So we can use this, for example, if I have 1 over Z, right? And I multiply it by, say, Z bar over Z bar, what do I get? Now, I'm not proving all these things. Like, I worked this out in more detail in the complex variables course, for example. Or at least I make you do it in homework. The point is, this you could rewrite as something, it's basically something in Cartesian form. It's like a real number plus I times another real number. So this is, again, a complex number, right? So this actually shows you how to calculate the reciprocal of a complex number. Let me make it a little bit less abstract. So suppose I want to calculate what's the multiplicative inverse of, say, 2 plus 3i. I mean, you don't think about it much, right? If you have 3, how do you find the multiplicative inverse of 3? It's 1/3, right? If you've got 2 plus 3i, how do you find the multiplicative inverse? Well, you have to use this little trick here, right? I mean, basically, you do 2 minus 3i divided by 2 squared plus 3 squared by this right up here, right? And so there you have it. 2 squared is 4. 4 plus 9 is what? 13? So it's 2/13 minus 3/13 times I. There you go. That's the multiplicative inverse of that complex number. That's how you do it. Simple as that. Besides that, you pretty much just do algebra like usual. So if we have an example which has complex numbers, don't be afraid. Just follow what you know and be aware of this issue. I mean, there's some other kind of funny stuff, right? Like, how about this? I times I is equal to -1, right? So what's that tell us about 1 over I? Yeah, it's negative I. That's a little bit disturbing, but there it is. Of course, having a number that squares to be a negative number is also a little bit unusual, right? But that's a complex number. Of course, the weirdity, although there's some oddity to these number system, right? But it does pay off big, right? We can factor any polynomial into a distinct up to you take any polynomial, you can completely factor it over the complex numbers, right? For example, the quadratic equation, right? Oh no, if it's a real quadratic equation, we can't solve it 1/3 of the time, right? We don't have that problem if it's a complex quadratic equation. There's always a solution. So that's complex numbers in a nutshell. This is one of the things I'm working on in the notes. I just want to write like a short page or two just to kind of say what I said here and then add a little bit more structure. So I'll try to do that for you guys. Because I know not everybody has recently, everyone should have seen complex numbers in high school, but it's been a little while for some of us, right? So, or maybe maybe your high school math teacher had some kind of aversion to complex arithmetic and refused to cover it. I don't know. Let's see here. The other thing we'll talk about a little bit is the case of modular arithmetic. Now, modular arithmetic is even a little bit different. So we'll talk about the set, say, Z mod NZ. And the notation I'm going to use in here is something like this: 0 bar, 1 bar, 2 bar, n minus 1 bar. So technically speaking, these are equivalence classes of integers or something. Who cares? The point is, these are objects, and I'll show you how to work with them. So here's the definition, basically. First of all, if I have x bar, it's equal to x plus any multiple n, any integer multiple of n. So here, so n is fixed throughout this discussion. We pick a world to calculate in. It could be mod 5, it could be mod 3, it could be mod 4, whatever it is. N is fixed, and then, but the rule is you can add any copy of n, multiple of n to something, and it doesn't change the object, all right? The other thing then, of course, is just this. If I have x bar plus y bar, I get x plus y bar. And if I multiply these, I can just multiply the representatives like that. So these are all essentially definitions. Can you guys think of anything else that I should tell you about modular arithmetic right off the top here? I think those are the essential features. I mean, there's questions that are begged here. How do I know those definitions are well defined, right? But you'll talk about that in other courses. I'm really just going to use it as an example in here. So just to give you an example then, so let's look at, say, Z mod 3Z. So in here, you got your 0, you got 1, you got 2. That's it, right? And so you can make a multiplication table, right? You can make like an addition. What do you guys want me to do, addition or multiplication? It's your choice. Multiplication? Okay. So I have 0 bar, 1 bar, 2 bar, 0 bar, 1 bar, 2 bar. It does seem rather wasteful to have written the 0 column and row in here, because obviously if you multiply 0 times, 0 multiplied by anything gives you back 0 again, right? 1 times 1 is 1. 2 times 1 is 2. 2 times 1 is 2. And then here we get 2 times 2, which is 4 bar. But we don't write 4 bar, all right? So our convention is, that's okay to write in an intermediate calculation, but for like the presentation of answers, to be nice and neat and tidy and stuff, we'll go back to one of these, right? Which is what? This is 4 is what? It's 1 plus 3, right? And in mod 3 world, 3 is 0. So basically, we can drop copies of 3. So this is just 1. So what this, by the way, shows is that in this world, so in this context, 1 over 3 bar is equal to what? Oh, I'm sorry, 3 bar, listen to me. That would be very bad, right? 1 over 3 bar is like 1 over 0. That's division by 0. That's still bad, even in this weird new world of modular arithmetic. So 1 over 2 bar, see 2 bar times 2 bar, what's this tell? This, let me just, what we're saying here is 2 bar times 2 bar is equal to 1 bar, right? Now 1 times anything is still the thing again. I mean, that's the way 1 bar works, so it's really the multiplicative, so-called multiplicative identity for this set, right? So in other words, 2 bar is its own reciprocal. Now, you've actually worked with modular arithmetic before, right? You guys tell time, right? We work mod 12 or sometimes mod 24 all the time, right? We identify 4 o'clock with one day from the next and so forth. Let me just do another example of that. Let's look at Z mod 6Z. So this is a little bit different. I won't try to write the whole table. I'll just write some examples. How about that? So how about if I have 3 bar plus 2 bar, what do I get? Yeah, that's just exactly 5 bar, which is one of our standard things, right? 3 bar plus 4 bar is what? It's 7 bar, which we subtract a copy of 6 off. We get back to what? 1 bar, right? All right. Addition is, I mean, no one has trouble with addition pretty much. I mean, that's kind of okay, whatever. I guess there is some kind of surprising things here, right? Like, for example, 1 bar plus 5 bar is equal to what? 6 bar, which is what? Right? So that tells us that the additive inverse of 1 bar is actually equal to 5 bar. That's kind of weird. But kind of not, right? I mean, if you think about going backwards or forwards on a clock, you know that you can either go forward to the time or back to the time. There's always this kind of interplay. But anyway, I digress. Multiplication. So let's see here. How about see if we can find, can you think of one that's kind of like the 2 bar in the last example where we multiply something and we get back to 1? One bar, I should say. What if I look at how about 5 times 5? How about 5 times 5? What's that? I try to sometimes I'll put a little space in the notes, or I put a little dot here. That's just to denote multiplication because I don't want you to. I mean, I know there's a temptation to think it's 55 bar. So I mean, I don't know. It's notational. But on the other hand, I don't want to draw in 4 parentheses because it's a hassle. So what is this? This is 25, right? Which is what? Subtract what? 24 is 4 times 6, right? So this is really, so therefore, 1 over 5 bar is equal to 5 bar. All right. Now, Z mod 6Z, all right, is not nice in the sense that Z mod 3Z is. In 3Z, there really was what? There was number 1 and number 2. right? 2 has a multiplicative inverse, which was 2. 1 had a multiplicative inverse, which is just 1 itself, right? So every non-zero thing in Z mod 3Z had a multiplicative inverse. That's why we would say that Z mod 3Z is what's called a field, right? In a field, you have a multiplication, you have an addition, and every non-zero element has a multiplicative inverse, right? That's not going to be the case with this thing because there's something really weird that happens with 3 and 2. Check it out. So like 2 bar times 3 bar is equal to what? 6 bar, which is 0, right? So that tells me that 1 over 2 bar and 1 over 3 bar don't exist in the usual way, right? I mean, I'm making a little bit of a jump there. I'm claiming that if that happens, there is no multiplicative inverse, right? That could be maybe like a nice little homework problem or something. So if this happens, right, if you have non-zero things, which when you multiply, you get 0, this makes 2 and 3 what are known as what? These are so-called zero divisors. All right. So the trouble is Z mod 6Z has 0 divisors. We can't find fraction. We can't reciprocate all numbers in Z mod 6Z. All right. That means if we tried to do what we're doing this semester on this set, it would be much more complicated because we can't divide. So what we want to do in here is we want to work in a set of numbers where we can divide. So for the most part, we're going to, once we get into the more serious stuff, we'll be working with fields. And the reason we do that is because in a field, we can always divide by a non-zero number. Whereas something like this, you've got annoying things like this. So it makes things like factoring more complicated, right? You have the product of two things is 0. You'd like to say one of those two things is 0. Here you can't. It's weird. All right, so that said, the first arc in this course is just about matrices and how to add them and multiply them, right? Turns out we can add and multiply matrices with entries taken from something other than a field without any extra trouble. Only later, once we start doing what's called row reduction, we start doing division, and there it becomes important to just work with fields. So the structure that I have chosen this semester is to try to tell you guys a little bit about abstract sets and groups and things. And so the first maybe few sections of the notes are just about working with matrices from things taken from what's called a ring, all right? Let me just say a little bit more about this terminology. Have you ever been exposed to this terminology before? Like what's a group, what's a ring, what's a field? Anybody? No? So the larger program of Math 421 and 422, Abstract Algebra 1 and 2, is really to educate you guys and make sure that you know what's a group, what's a ring, what's a field, and to make you proficient in working with those things. So here I'm just really using it as a language. We're not going to get very deep into it, but basically this is it. G is a group. Just means what? It means that G is a set with an operation called multiplication. All right. You could call it addition as well, but let's just call it multiplication for the sake of discussion today. It could be multiplication, it could be addition. It's got an operation. Let me tell you what, it's a set with an operation. There we go. No, I'm not poisoning the well. It's a set with an operation. That operation has to have a few important items. Basically, there's an inverse. First of all, there's an identity for the operation, like 0 for addition or like for 1 for multiplication. And every element in the set has either an additive inverse or a multiplicative inverse. There's an inverse to each element according to the operation, and the operation's associative. Right? So basically, those 4 things. Operation means that if you take 2 things, you operate on them, you're back in the set again. That's a group. That's all a group is. Those 4 things. It's a set with an operation which is unital, closed under inverses, and associative. So that's a group. We don't really, we touch on it. We do find our way looking at groups in certain examples, but that's not the focus, all right? That's just really something, every once in a while we'll stumble our way into looking at something that's a group of things. It's just basically name calling for us. We're like, oh, look, that's a group. You know, that's kind of it. We don't study the general properties of groups in here. That's Math 421. R is a ring. What does it mean for R to be a ring? So basically a ring is actually a triple. It's R with an addition and a multiplication. But the multiplication we usually juxtaposition for. So let's see here. If I have A, B, and C in the ring, we have the following. There's a 0 in the ring, such that like x plus 0 is equal to x for all x in the ring. This plus is like addition. It's in a commutative operation. So like x plus y is y plus x. So it's got a 0 for each. Man, I don't want to write all this out. What have I got myself into? For each x in R, there exists minus x in R, such that x plus minus x is equal to 0. X plus y is equal to y plus x for all x and y in the ring. X plus y plus z is equal to x plus y plus z. Again, for all elements in the ring. Okay, so these first three things I just wrote collectively, these mean that if you just look at the ring with the addition, it's what's called an abelian group with respect to the addition. In other words, the addition operation, it acts like addition usually works, right? A plus B is B plus A. There's something called 0 that if we add it to anything, we get back where we started. And you can always take something and find its additive inverse, right? For every 5, there's a minus 5, right? And so forth. But that's not all a ring is. A ring also has a multiplication, and the multiplication just works like multiplication usually works. You guys know what multiplication is, right? The star usually just, so we can say A star B. Usually we just write AB for the multiplication. So that notation, oh, somebody else is crazy enough to lecture today. Interesting. So this notation is called juxtaposition, right? So A times B is A times B. And what rules do the multiplication have? Well, there's a 1. There can be only 1, right? So there's 1 in the ring, such that 1 times x is equal to x for all x in the ring. Curious. So that number 1, of course, is called the multiplicative identity. And what else do we have? Well, x times a plus b is equal to what? And x plus y times a is equal to what? So you said xa plus xb. Now you changed the order of x and b with what you just said, which would be fine if this was also what's called a commutative ring. So in a commutative ring, we have the additional relation that multiplication commutes. And that's not a bad thing for you to have said, because we are pretty much only working with commutative rings in here. And now over here we got what? Yeah. So these are the so-called distributive properties, right? And also multiplication's associative. So it's an associative, it has distributive properties, there's a multiplicative identity, all right? All of this structure is assumed for the multiplication in a ring. So a set with 2 operations is called a ring. For example, this is a ring. Z mod 6Z is a ring because it has an addition and it has a multiplication, and the multiplication will satisfy the ring axioms. Okay. I've probably forgot some axiom. That actually is somewhat carefully written in the notes. I don't really expect you guys to memorize the ring axioms just yet. It's for your informational purposes at the moment. Part of my way of teaching math is to try to put things in their larger arena, right? And so you have to understand, the homework will kind of show you more what you must master as opposed to what I'm just telling you for informational purposes. So now, a integral domain. What's an integral domain? In an integral domain is a ring with no zero divisors. A ring with no zero divisors. So looks like this one's out of luck, right? This is not an integral domain. Z mod 6Z is not an integral domain because we have zero divisors. What's an example of an integral domain? How about the ring of integers? The ring is, are the integers a ring, by the way? If you add two integers, do you get an integer again? Yep. If you multiply two integers, do you get an integer again? Sure do. There's multiplicative identity, it's 1. The additive identity is 0. Right? Addition and multiplication, as we standardly define them, fit these abstract definitions of addition and multiplication. And finally, if you have product of two integers is equal to 0, of course that forces either a or b to be 0, right? You can't have a product of two integers be 0. So, in fact, the integers are a integral domain. That's probably where the word integral comes from, like integers. In the finite case, this is also an integral domain, right? There were no zero divisors for Z mod 3Z. But you said, but I also told you that Z mod 3Z was a field, right? Every non-zero element has a multiplicative inverse, right? That's a field. So apparently in the finite case, there's a connection between integral domains and fields, right? In fact, it's true that if you have a finite ring, if it's an integral domain, then it's a field. In the infinite case, the converse is true. It's always true that if you have a field, it's automatically an integral domain, right? Because if something has a multiplicative inverse, it can't be a zero divisor. That's a simple thing. I'll make that a homework problem that's useful. It's like 2 lines. It's not a hard thing. You just need to have a question asked you clearly, not just mumbled at the end of a, silly lecture. So integral domain, field, ring. That's the basic language that we need as a backdrop. So for the most part, in the next 30 or so minutes of lecture, I'll be talking about a commutative ring. All that means, all right, strip it away, all it means is there's an addition, there's a multiplication, there's the number 1, there's the number 0, and things behave as normal. So every place, and I will typically use R in the notes for a commutative ring. All right, if I want to talk about an arbitrary field in the notes, we use this symbol. This is for field. So fields include the reals, the complexes, the rationals, and then Z mod PZ, where P is prime. It turns out if you're modding by a prime integer, it's a field. On the other hand, if you're modding by a composite number, the products in the composite will be zero divisors. Sharon's back? No, that's not the right laugh. All right. And then again, R is an integral. R is a ring just means, I usually will think about a commutative ring. There's tons of stuff that can be commutative rings. Z mod NZ for any n is a commutative ring. Integers, rational numbers, all your favorite, and pretty much everything is commutative. Well, everything, maybe not everything. Lots of things are commutative rings. matrices. All right, so that brings us to, finally, what I was trying to talk about today. Man, I was going to find a way to not say this in lecture, but I guess this stuff has to be said. I mean, there's two ways to teach this course, right? And maybe I'm teaching it the wrong way this semester. You guys can be the judge at the end of all this. In the past, instead of talking about a ring, I've just talked about real numbers at the start of the course, just real, right? And then towards the end of the course, I start saying, well, everything we did at the start, you could replace the reals with complexes, it would still work, right? But I think it's worthwhile to point out that we don't need to just use real numbers here. We could just as well use something from a ring. Part of the reason I'm saying that is because I want to draw your attention to the structure that we're using. And the structure that we're going to use is really just these ring properties. So with that, I bring us to the next question, which is, what is a matrix? Right? So we're studying matrices and their properties for a while in here. So a matrix, I would say a matrix is an array, all right? So it's a set of elements. It's not just a set of elements, it's an arrangement of elements in a certain order. So here's a typical matrix, something like this, A. So A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. So this would make this is an M by N matrix. So much like the Cartesian product I was talking about earlier, it has a notion of ordering things, right? So let's see here. The elements of the matrix, or rather the components of the matrix, so here, A11, A12, all the way on out to AMN, these are elements of some set, right? I don't want to be too specific. I'm just going to say S for set, right? These are called the components of A. All right? Nothing too surprised, I guess. It's not. It's what it is. Now, let's see here. If I talk about A, I, J, just abstract notation, this I is called the row index. The J is called the column index. All right? And we have the pair I comma j, an element of what? So what? Because I is the first one. It goes from 1 to M. And then the second one, the J, goes from 1 all the way over to N. So M, as in mommy, is the number of rows. N, as in nanu nanu, is the number of columns. And there you have it. We can also talk about row or column, right? Like row 1, for example, of A is what? It's A11, A12, A1n. All right? What if I were to say row j, well, say row I rather. What would be the ith row of A? Instead of putting 1, I just put, yeah, let me be lazier here. Everybody see that? Here, I will make it arbitrary, like so. Okay. Ooh, and I'm giddy with this newfound color coding. Let's try columns. By the way, I should warn you, the start of my course is always the worst part. At least I always think it's the worst part. I'm not sure which is the worst part. Lorenzo's like the final. Let's see here. No. A 1 1, A 2 1, dot dot dot, A M 1. This would be the first column. I mean, you can see that. That's the first column, right? Column 1. Here was row 1. Oops, that's not good. Not a good move for my color coding. Here. Row 1. Column 1. All right, now to get column I do what? Just okay. So in a column vector, the column index is fixed. In a row vector, the row index is fixed all the way through it. All right. Now, a lot of times we like to talk about where things are. Where is A? A is an element of S m by n. So what I'm trying to tell you there is S m by n, that's the set of all m by n matrices with elements taken from S. All right? Any questions so far? All right. Now, I mean, there's examples abound, right? For example, we could have 1, 3 plus I, 0, 2. I could have B equals to 1 bar, 2 bar, 7 bar, 20 bar. I could have C equal to F, G, H, 0. Now, this would be an element of complex 2 by 2 matrices. This is totally ambiguous until I tell you what the bars are, right? That's the bad thing about this bar notation, right? If you study these things more carefully, some people, instead of writing like k bar, they would instead write k plus n z for the equivalence class. That's actually what it is. It's a coset under addition. I'm saying things you don't know. Sorry. The point is that you don't know which n, right? So it's kind of up to, I mean, we can just say n equals to what? How about 31 there? So this would be in, say, Z mod 31 Z 2 by 2 matrices in there, all right? Again, when P is prime, we can do almost everything we can do for real numbers or complex numbers in this other set as well. It's fun. Now here, I'm supposing that F and G and H are real functions. All right, so this would be an element of, say, let's say smooth functions on the reals. 2 by 2 matrix of real functions. Like, I mean, I could be more specific. I could say something like e to the x, sine x, you know, cosine x. You could look at a matrix of functions. You could do calculus on such things. In fact, it's not that hard. I'm almost done. One other thought, and then we'll stop for today. If A and B are elements of Sm by n, then A equals to B if and only if what? What is required for two matrices to be equal? Exactly, yes, yes. We must have that Aij is equal to Bij for all pairs I and j in the Cartesian product of n sub m by n sub n. Now, if you're really picky, you might notice I never really defined what a matrix was, right? I just said it's this array of things we can work with. And that's really where we're going to start in here, right? In the notes I explained, you could think of them as a set of functions from like n sub m cross n sub n into the set. Just like you could think of a sequence as a function from the integers into the real numbers. You could take that viewpoint for like a finite, kind of like a finite sequence. A matrix in some sense is like that. The point is that there is, the matrix takes ownership over its components. It knows which component's which. It doesn't get confused about which is 1, 1 versus which one is like 1, 2 versus 2, 1. Those are distinguished, generally speaking. It's essentially just a kind of a supercharged Cartesian product of some sort. I don't know. Anyway, thanks for coming today, guys. And I will see you Wednesday. And hopefully later today I'll have the syllabus and such posted. Thanks, guys.